pause the video, and by looking at this graph, I want you to state the relative maxima and or minima. So as an ordered pair, what is the maxima and minima? So hopefully you notice that the minima, once again, is going to be the lowest point surrounded by any other point. So if you look at the graph, it looks like that's at 4, 3. And then if you look for the maxima, that is going to be the highest point surrounded by other points. That looks like that's happening at the ordered pair 130. All right, so let's talk about inverse functions still. So we're still in section 2.7. Today we are going to find the inverse of a function. We're going to use the horizontal line test to determine if a function has an inverse. We can use the graph of a one-to-one function to graph its inverse function. And we're going to find the inverse of a function and graph both functions on the same axis. So let's talk about the horizontal line test and one-to-one functions. Let's see what happens if we try to find the inverse of a standard quadratic function f of x equals x squared. Remember, we would switch the x and the y around, and so then that would give us, well, first we'd have y equals x squared. We'd switch the x and the y around, so that would give us x equals y squared. But then to get rid of the squared term, we'd have to take the square root. And remember, when you take the square root, we would get then two solutions. We would get both a positive and a negative square root of x. So notice that here, because I would then plug in a value of x and get two values for y, that wouldn't be an inverse. I can't have that because that isn't a function. Okay, so remember, the plus or minus shows that for certain values of x, there were two values of y. And remember, that can't be a thing. So, solutions to f of x. Notice that if I was to plug in -2 into my original function and I square it, I get 4. When I plugged -1 into it, I got +1. When I plugged 1 into it, I got 1. When I plugged 2 into it, I got 4. If I tried to then look at the inverse that we just came up with, notice that I would then think about plugging in perfect square numbers. So like if I plugged 4 in underneath the square root, I would get not only +2, but I would get -2. When I plug 1 underneath that square root, I would get not only +1, but I would get -1. If you see that there's actually kind of a relationship between these two different sets of ordered pairs, notice that they're just flip-flopping, okay? The ordered pair for the inverse of f of x, which is -2, 4, when it flipped around to 4, -2, and then so on and so forth. That's not a coincidence, okay? So a function f has an inverse that is the function f inverse if there is no horizontal line no horizontal that intersects the graph of the function f at more than one point. Okay, so it says, which of the following graphs represent functions that have inverse functions? So remember, before we determined if we had a function if we used the vertical line test. Now we're going to determine if we have any inverse functions by doing the horizontal line test. So notice that if I start drawing horizontal lines, in part A, I see that I have, in the first horizontal line, it touches at 2 spots. In the second horizontal line, it touches at 2 spots. So that means that this does not pass the horizontal line test because it touches at more than one spot. So that means that this does not have an inverse function. So notice that this is our basic function for the absolute value of x. Notice that that's kind of similar then to what we just talked about on the last slide when we talked about the quadratic function when it was x squared, because it was like a shape of a U. So the v's don't work, the u's don't work. Those are not going to have an inverse function. If I look here at part B, every single time I draw a horizontal line, it's only going to touch that function one time. Same thing over here. If I draw a horizontal line, it's only going to touch the function one time. So both of these pass the horizontal line test, which means both of these have an inverse function. All right, let's talk one-to-one functions. A one-to-one function is a function in which no two different ordered pairs have the same second component. So basically, second component is our y value. So only one-to-one functions have inverse functions. Any function that passes the horizontal line test is a one-to-one function. Any one-to-one function has a graph that passes the horizontal line test. So notice that, once again, if it has no two different what's it say? No two different ordered pairs have the same second component. So going back once again to like that f of x equals x squared, we were getting the same second component. Like if I had -2 and I squared it, I was getting 4. But then if I took 2 and I squared it, I was also getting 4. So they were getting the same second component. And that's why we didn't have in this case, it wouldn't be a one-to-one function, which means it didn't have an inverse. Okay. So graphing the inverse function. So if we know that we do have a one-to-one function, it passes the horizontal line test. Okay, we are going to be able to graph not only the original graph, but also the inverse function. So there is a relationship between the graph of a one-to-one function f and its inverse f inverse. Because inverse functions have ordered pairs with the coordinates interchanged, like I showed you in the last or a couple slides ago, okay, if I switch the x and the y, I'm going to get the inverse function ordered pairs. So because inverse functions have ordered pairs with the coordinates interchanged, if the point AB is on the graph of f, then the point BA is on the graph for the f inverse. And so as you keep interchanging those ordered pairs, we are going to have a reflection on the line y equals x. So here's a little diagram over here to the right showing you that if I have the blue graph, which is just my f, and my green graph, which is my inverse of f, notice how they are going to, if I was to fold that line, y equals x, the function f and the inverse function, well, that would fold nicely one on top of the other. All right, so let's look at this example. It says the graph of the function f consists of two line segments. One segment goes from -2, -2 to -1, 0. So let's do that first. -2 is down here. -1, 0 is right here. So there is one segment when I connect that. And then the second segment goes from -1, 0 to 1, 2. So here is then the second. So that whole thing right here, that's my f of x function. So we just graphed the f function, and now they want us to graph the inverse function on the same graph. So remember, if I have my ordered pairs for my original function, that means that my inverse function is going to be containing the ordered pairs flipped around. So -2, -2, flipping it around, it's still going to be the same thing. So that's going to be an ordered pair on my inverse. -1, 0. When I flip that around, that means that 0, -1 is going to be a point that is on my graph. So let's start with that because that's one line segment. So -2, -2 is still right here. But then 0, -1 is right here. So that's half of my inverse function. There's my first line segment. And then from that now, 0, -1, it's going to go to the ordered pair. When I flip 1, 2, it turns into 2, 1. So that's this right here. Oops, I got to connect that better. All right, so notice that that is, oops, not g of x, but that's my inverse function. Okay, notice that if I was to look at my y equals x line, my graph for my f of x function would fold nicely on top of my inverse function. So that tells me that I graphed this correctly. Okay, so when they're giving you ordered pairs, it's pretty easy to determine what your inverse function ordered pairs are going to be. You're not always going to have that. So this time I want us to look at the inverse of f of x equals x squared plus 1, but this only happens if my domain has x greater than or equal to 0. Okay, we're going to graph the function f and then the inverse function on the same rectangular coordinate plane. Then we're going to state the domain and range of our functions. All right, so notice that because this is an x squared term, normally we then would have a u, but remember, we can't have a full quadratic and have it be an inverse. So that's why they cut that domain in half. It's really going to not have any negatives. It's going to essentially like start at that, and it's going to turn into like half of a u. All right, so what I'm going to do is I'm going to plug in some numbers. Okay, so in my, I'm sorry. I got to have my x values be greater than or equal to 0. So I'm going to start at 0. I'm going to do 1, 2, and let's even do 3. All right, so if I square 0, it's still going to be 0, but then I have to add 1 onto it, so that gives me 1. Square 1, I get 1, add 1, I get 2. 2 squared is 4, add 1, I get 5. 3 squared is 9, add 1, and I get 10. So those are the ordered pairs for this original function f of x. So I'm going to plot those points. So 0, 1, then 1, 2, 2, 5, and 3, 10. So there is my function f of x. Now I can take the table that I just created, and I know that my inverse function is just going to be flipping those ordered pairs around. So it's going to be 1, 0, and 2, 1, and 5, 2, and 10, 3. So I don't have to do any extra calculations. Once I know what the ordered pairs are, just flip them around. So 1, 0, 2, 1, 5, 2, and 10, 3. That's this right here. There is my inverse function. Okay, once again, you can draw it if you want. Here, I'm going to draw it. Our line y equals x. Notice that if I was to fold my graph over that line, I would be getting my two functions that I just graphed to fold nicely one on top of the other. Okay, so now it's asking for us to state domain and range for each. So let's start with the f of x function. I know that my domain is going to, based off of my restrictions, remember domain deals with the x values. So it's going to start at 0, it's included, and it can continue to go and go and go, so it's going towards infinity. If I'm looking at the range, I'm looking at my y values. Notice that the first spot is at +1 and it's included, and then it's going to continue to go up towards positive infinity. Okay, so now I want to look at my inverse function. So the domain is going to be the x values. Well, notice that I'm starting at 1 and it's included and it's going towards positive infinity. If I look then at my range, which are my y values, well, it starts at 0 and it's included and it's going towards positive infinity. So essentially notice that my range for my f of x was my domain for my f inverse. And my range for my f of x, no wait, did I say that backwards? And my domain for my f of x is my range. So the domains and range flip when we are stating the function versus the inverse function. So that's us dealing with the inverses, looking at horizontal line tests, talking about one-to-one functions, and then being able to graph on the same graph or on the same axis.